This story is about the universe we see and the universe that remains beyond our gaze. About the strange nature of any observation. When we look at the sky, we see not the present, but the past. This is not a metaphor or a philosophical generalization. It is a physical property of light, time, and space. And that is why everything we know about the cosmos is based on something that no longer exists. What is at stake here is our very idea of reality. We are used to thinking that science knows a lot: the sizes of galaxies, the ages of stars, the laws of motion. But behind this confidence hides a troubling fact. Most of the universe's contents are invisible. Scientists call it dark matter and dark energy, and these names are not explanations, but confessions of ignorance. Visible matter, stars, planets, clouds of gas, makes up only a tiny fraction of everything that fills space. Moreover, observation itself has a boundary, a horizon that no gaze will ever cross. Expanding space carries distant galaxies away so quickly that their light will never reach us. We are observers locked in a finite domain, and this domain does not grow with time. It shrinks. What we could have studied yesterday will be forever out of reach tomorrow. And that raises a simple but unsettling question. How complete is the picture we build from such a limited slice? What do you think? Is it possible to truly understand the universe if most of it is hidden from us by its very nature? What matters more in this conversation? The persistence with which science gathers fragments of knowledge, or the humility before what can never be seen? Listen, this story is about that, about the limits of sight, about invisible matter, about time that carries light beyond the horizon, about a universe that remains a mystery even when we know its age. Everything we see in the night sky is the past. The nearest stars appear to us as they were many years ago, and galaxies as they existed long before complex life appeared on Earth. The farther away an object is, the deeper into the past our observation reaches. And in this sense, every telescope is a kind of time machine, a tool not only for spatial, but for historical exploration. The concept of the observable universe does not coincide with the concept of the universe as such. In scientific language, the observable universe is the part of the cosmos from which light and other signals have had time to reach Earth during the existence of space in its current state. This definition introduces several limitations at once. It ties our knowledge not only to the structure of matter, but also to the finite speed of information transfer and to the history of space-time itself. Light is not an instantaneous messenger. It travels at a maximum speed, the same for all observers. And so any observation always refers to the past, not to the state an object is in right now. The observable universe has a boundary, commonly called the observation horizon. Beyond this boundary, there may exist galaxies, structures, and various forms of matter, but their signals have not yet reached Earth. The reason for this lies not only in distance, but in the expansion of space itself. Remote regions become less and less accessible to observation over time, and the light emitted from there stretches along with space, losing energy and shifting toward longer wavelengths. Its wavelength increases, its intensity weakens, and at some point the radiation can no longer be detected. This expansion should not be imagined as matter flying apart in empty space. In modern cosmology, it is the expansion of space-time itself. Galaxies, on average, are not moving through space at enormous speeds. Instead, the scales of distance between them are changing, and matter is simply carried along with the space in which it resides. This description is confirmed by observations of the spectra of distant objects, in which spectral lines are shifted toward longer wavelengths, and this shift is interpreted as a consequence of the stretching of space, not as a simple effect of motion in the classical sense. The observable universe is thus not just a collection of objects, but a slice of dynamic history, a picture unfolded in time, whose size is determined by the age of cosmic expansion and the properties of space itself. Current estimates suggest that the diameter of the observable region greatly exceeds the simple product of the speed of light and the age of the universe. This is because space has expanded and continues to expand, so the objects whose light we see today are now much farther away than the distance that light traveled in the past. But here is the strange thing. This limited fragment of the universe looks astonishingly similar in all directions. On large scales, the distribution of galaxies is remarkably uniform. The cosmos displays similar statistical properties in every direction. This does not mean that matter density is exactly the same at every point, but it does indicate the absence of a special center or privileged direction. This picture underlies the cosmological principle, which states that the universe is, on average, homogeneous and isotropic. This principle is not an obvious consequence of everyday experience. On small scales, the universe is extremely inhomogeneous, with stars, planets, gas clouds, galaxies, clusters, and vast voids. But as the scale increases, the differences gradually smooth out. And the reason for this transition from complex structure to statistical simplicity is not fully understood. There are theoretical models linking this property to the early stages of cosmic evolution, but direct observation of these processes is unavailable. They unfolded in conditions that current instruments cannot reproduce or directly detect. An additional complication is that the observable universe includes not only visible matter. Measurements of the motion of galaxies and their clusters show that the matter we see is insufficient to explain gravitational effects. This led to the introduction of the concept of dark matter, a component that does not emit light and does not interact with electromagnetic radiation in the usual way. Very little is known about its nature, but its influence on the structure of the observable universe is considered significant. In addition to dark matter, cosmology uses the concept of dark energy. This term refers not to a specific substance, but to a form of energy associated with the accelerated expansion of space, the nature of which remains one of the deepest mysteries in modern science. If you look at the universe from a great distance, it appears the same in every direction, with no special center and no privileged point. Yet most of its contents remain a complete mystery to us. How do you measure the age and size of something you can neither see in full nor touch? These parameters are not measured directly. They are inferred indirectly through a combination of observations, theoretical models, and assumptions that link observable quantities to physical processes. That is why even such seemingly basic characteristics remain the subject of scientific debate and constant refinement. The age of the observable universe is tied to the beginning of cosmic expansion. This beginning should not be understood as an explosion in pre-existing space. Modern descriptions are based on the idea that space-time itself was once in a state of extremely high density and temperature, after which it began to expand. In this picture, the age of the universe is determined by how much time has passed since the conditions became such that the known forms of physical laws became applicable. Different methods are used to estimate the age, one of which is based on measuring the rate of expansion, expressed by the Hubble parameter. This parameter links the speed at which galaxies recede to their distance. Knowing its current value and assuming a certain model of expansion evolution, one can calculate the corresponding time interval. Two completely independent ways of measuring the rate of expansion give different answers, and this difference does not disappear. In fact, the more precise the measurements become, the more clearly the discrepancy appears. Some measurements rely on observations of nearby galaxies and stellar systems, where distances are estimated using a chain of calibrations, each link based on the previous one. Others use properties of the cosmic microwave background, which carries information about the early state of the cosmos. These two approaches, being independent, yield values for the expansion rate that do not agree within the expected uncertainties. This discrepancy is known as the Hubble tension, one of the main unresolved mysteries of modern cosmology. Its cause is still unclear. It may point to unaccounted for systematic effects, or to the need to revise certain aspects of the cosmological model. Either someone is making a systematic error, or there is something fundamentally wrong with the standard picture of the world. The scale of the observable universe is also not determined directly. It is related to the maximum distance light has been able to travel, taking into account the expansion of space. It is important to distinguish between the distance light has traveled and the current distance to the source. Due to expansion, these quantities differ significantly. Light may have traveled for billions of years, while the object that emitted it is now much farther away. Cosmology uses several definitions of distance: light travel, proper, angular, photometric, each convenient in a certain context but none universal. Confusing these concepts can lead to incorrect conclusions about the size and structure of the cosmos. Another puzzle is the relationship between the age of the universe and the ages of individual objects. There are stellar systems whose estimated ages are close to the age of the universe itself. These estimates come from models of stellar evolution, which depend on chemical composition, mass, and other parameters. In the past, there were cases when the age of some objects seemed too great, and such cases prompted a revision of both astrophysical models and cosmological parameters. The question of whether anything existed before the beginning of expansion within the standard model lies beyond the applicability of known physical theories, and many researchers see this as a sign that the theory ceases to work in these conditions, not as evidence of a real physical beginning. And yet, galaxies do not simply fly apart chaotically. They gather into colossal structures visible only at the largest scales. Between galaxies are voids hundreds of millions of light years across, regions of near absolute emptiness that separate a complex network of filaments and nodes. Galaxies are distributed neither randomly nor strictly uniformly. They form a branching web of elongated strands, intersections, and vast regions of very low matter density. Mapping the distribution of galaxies reveals that they group into clusters and superclusters, connected by extended structures between which galaxies are rare or nearly absent. The sizes of these voids can reach hundreds of millions of light years, and they are not absolutely empty. Their matter density is simply much lower than average. Their existence is a hallmark of the observable cosmos and a source of questions about the mechanisms of structure formation. The formation of this structure is linked to initial density irregularities in the early universe. These irregularities were minuscule in amplitude, but under gravity they gradually grew. Regions with slightly higher density attracted more matter, becoming increasingly massive, while regions with lower density emptied out. This process continued for billions of years and ultimately led to the web-like structure we see today. Numerical simulations based on known laws of gravity and properties of dark matter successfully reproduce the overall picture, but in detail, there are discrepancies. For example, the distribution of galaxies within voids and at their boundaries sometimes differs from theoretical expectations, which may indicate either incomplete models or unaccounted for physical properties of cosmic components. Cosmic voids are interesting not only as traces of structural evolution, but as possible laboratories for testing fundamental laws. In regions of low matter density, gravitational effects manifest differently than in galaxy clusters, allowing alternative theories of gravity to be tested, as well as evaluating how universal conclusions drawn from denser regions really are. Observing voids also depends on which objects are used to map the cosmos. Different types of galaxies may fill space differently, and the picture of structure is partly determined by the properties of the chosen indicators. Accounting for this effect requires careful statistical analysis and comparison of data from different sky surveys. The question of the exact scale at which matter distribution becomes homogeneous remains a subject of debate. Some studies point to structures whose sizes are comparable to the presumed scale of homogeneity, though this does not necessarily contradict the cosmological principle and requires more precise analysis of the statistical properties of galaxy distribution. The large-scale structure of the universe is the result of a long and complex evolution, preserving information about initial conditions, cosmic composition, and the properties of fundamental interactions. Much of this information is encoded in statistical patterns, not in individual objects. All of this structure, filaments, clusters, superclusters, is held together by something we neither see nor understand. Scientists know quite precisely how much dark matter there is in the universe and how it is distributed among galaxies and clusters. They know that without it, no galactic structures could exist as we observe them. But what exactly this dark matter is, no one knows. The first hints of the problem appeared when studying the motion of stars and galaxies. Their rotation speeds around galactic centers were higher than expected, given only the mass of visible stars and gas. Similar discrepancies were found when analyzing the motion of galaxies and clusters. Gravitational attraction was much stronger than visible mass could explain. Observations showed that the gravitational effect clearly exceeded what visible matter could provide. One of the key arguments for the existence of dark matter is gravitational lensing. Mass curves space-time, and light from distant objects bends as it passes near massive structures. By measuring the degree of this curvature, one can estimate the mass distribution without relying on emitted light. And in some cases, such measurements reveal significant mass where visible matter is clearly insufficient. According to modern models, it is dark matter that forms the primary gravitational frameworks into which ordinary matter later falls. Without this component, the growth of irregularities would be too slow, and the structure of galaxies we see today simply would not have had time to form. Despite the importance of this component, its nature remains unknown. Some models propose that dark matter consists of new elementary particles not included in the standard model of physics, stable, electrically neutral, and weakly interacting with ordinary matter. Other approaches consider more complex scenarios, including whole families of particles or new forms of interaction. There is also an alternative idea that on large scales, the laws of gravity differ from the familiar ones. In that case, no extra mass is needed because the description of attraction itself changes. However, such approaches struggle to match the full spectrum of cosmological data. Experimental searches for dark matter particles, conducted by various methods, have not yet yielded a definitive result, and this keeps the nature of this component uncertain. Dark matter also affects the dynamics of satellite galaxies and the stability of galactic disks. Observations show that without an additional gravitational framework, many galactic structures would be unstable. At the same time, the distribution of dark matter on small scales remains an open question. Numerical models predict a certain density profile in galactic centers, but observations sometimes indicate smoother profiles. This discrepancy may be related to the physics of dark matter itself or to the influence of processes in ordinary matter, such as star formation and energy release. Thus, dark matter remains both a necessary element of the modern picture of the universe and a source of fundamental uncertainty, shaping the structure and evolution of the cosmos while remaining inaccessible to direct observation. If dark matter invisibly holds galaxies together, something else makes them fly apart ever faster, and that something is even more mysterious. The expansion of the universe is not slowing down, it is accelerating. For a long time, the opposite was expected. The gravity of all the matter in the cosmos should have gradually slowed the expansion. But observations of distant astronomical objects painted a different picture. Studies of certain types of supernova explosions allow them to be used as standardized light sources. Comparing observed brightness with the expected value show that distant galaxies are farther away than they would be in a decelerating expansion model. This led to the conclusion that the rate of expansion is increasing over time, and the concept of dark energy was introduced to describe this phenomenon. Dark energy is not energy in the everyday sense, but a general term for an effect seen in the dynamics of spacetime. The simplest way to describe this effect is the cosmological constant, which appears in the equations of general relativity. In this approach, dark energy is associated with the energy density of the vacuum, uniformly filling space. However, attempts to match the observed acceleration with quantum ideas about the vacuum run into serious difficulties. Theoretical estimates of vacuum energy density from quantum field theory are vastly greater than the observed value, and this discrepancy is considered one of the deepest problems in modern physics. Quantum physics calculations give a value for dark energy density that catastrophically disagrees with what we actually register. Besides the cosmological constant, there are other models of dark energy. In some, a dynamic field is assumed, whose properties may change over time and space. Such models allow for the possibility that the acceleration of expansion is not constant and may have a complex evolution, though observational data so far do not allow us to distinguish these scenarios with confidence. Dark energy has a noticeable effect only at the largest scales. Within galaxies and their clusters, its effect is negligible compared to gravity from matter. That is why accelerated expansion becomes apparent only when analyzing the distribution of distant objects in the cosmic microwave background. This makes dark energy difficult to study and increases the uncertainty in its interpretation. There is also a viewpoint that accelerated expansion may be due not to a new component, but to changes in the laws of gravity on cosmic scales. Such theories introduce additional terms into the equations describing spacetime and are actively studied, but they struggle to match observations in denser regions of the cosmos, where classical gravity is well confirmed. Dark energy is closely tied to the future of the observable universe. Its properties determine whether expansion will continue forever, accelerating, or change its character. If dark energy continues to act with the same strength, distant galaxies will gradually disappear beyond the observation horizon forever, and the possibility of studying them will be lost. But we do have a snapshot of the universe's early state, from a time before there were galaxies, stars, or even neutral atoms. The cosmic microwave background is light that has traveled through the universe since it was a dense, hot plasma. It carries information about the state of the world before the first stars appeared, and in its faint irregularities is encoded the origin of all galaxies and large structures. Its discovery was a key event in the development of cosmology, as it made it possible to study the state of the cosmos at a time when familiar astronomical objects did not yet exist. This is a faint microwave background coming evenly from all directions. In the early universe, matter was in a state of hot, dense plasma. Electrons in atomic nuclei constantly interacted with photons, making space opaque to radiation. As the universe expanded and cooled, a moment came when electrons could stably combine with nuclei to form neutral atoms. And after that, photons could travel freely. The radiation that arose during this period is observed today in a much cooled form. Its spectrum is close to that of a perfect black body at very low temperature, indicating a near-thermal equilibrium state in the early universe. Such equilibrium is hard to explain without assuming a close connection between different regions of the cosmos at early stages. And this itself raises questions about the mechanisms that established such uniformity. Although the cosmic microwave background is almost the same in all directions on average, it contains extremely small irregularities. These deviations from the mean reflect the initial density fluctuations. These are considered the seeds of future galaxies and clusters. Studying the statistical properties of these irregularities allows us to extract information about the universe's composition and the parameters of its evolution. Measuring the cosmic microwave background is done with high precision and requires accounting for many factors, including the influence of our own galaxy and instrument effects. Despite this, different experiments yield consistent results, strengthening confidence in the overall picture. Nevertheless, some features of the irregularity distribution raise questions. In particular, possible anomalies on the largest angular scales are discussed, which may indicate either statistical fluctuations or deeper effects. Interpreting the cosmic microwave background relies on theoretical models of the early universe. One such idea is the hypothesis of an extremely rapid expansion phase at the very beginning. This is introduced to explain the uniformity and isotropy of the observed background, as well as the origin of initial fluctuations. However, there is no direct observational confirmation of such a phase, and its parameters are inferred indirectly. There is also an alternative view that the properties of the cosmic microwave background can be explained without invoking an extra expansion phase, by means of special initial conditions or new physical effects. The cosmic microwave background also serves as a benchmark for checking the consistency of cosmological parameters, linking together the density of matter, dark energy, and the curvature of space. Small discrepancies between parameters obtained by different methods persist and require careful analysis. They may point to the limits of measurement accuracy or to the need to refine models. But even this radiation and the entire observable cosmos are accessible to us only up to a certain limit, beyond which observation becomes fundamentally impossible. In the distant future, intelligent beings in our galaxy may look at the sky and see only emptiness. All other galaxies by then will have disappeared beyond the observation horizon forever, with no way to return. The observable universe does not expand for the observer, it contracts. The observation horizon defines the boundary beyond which events cannot affect current observation. Light and any other carriers of information from those regions have not yet reached the observer. This boundary is not a material object or barrier, it is a surface in space-time, dependent on the history of the universe's expansion. Over time, the position of the horizon changes, but not all regions become accessible to observation. In an accelerating universe, an additional type of horizon arises, related to the future. There are regions from which light emitted now or in the future will never reach Earth. The reason is that the space between the source and observer expands too quickly. Even if the signal starts moving in the right direction, space itself grows so much that the distance to the source keeps increasing. This leads to a paradoxical consequence. The observable universe does not increase in the amount of accessible information. It decreases. Distant galaxies gradually disappear from view. Their radiation becomes so stretched that it can no longer be detected, and in the end, only the nearest surroundings, gravitationally bound to the observer, remain. The existence of horizons raises the question of the completeness of cosmological knowledge. Even with perfect instruments, the observer is always limited to a finite amount of information, and any conclusions about the properties of the entire universe are inevitably based on extrapolation. The cosmological principle, which assumes homogeneity and isotropy, is used precisely as a means of such extrapolation, but its validity beyond the observable region cannot be tested. Horizons are also linked to the question of information loss. In an expanding universe, information about the state of distant regions may become forever inaccessible, and this is not only a philosophical, but a physical issue. The problem of horizons echoes discussions of entropy in the direction of time. The observable universe evolves so that the number of accessible states increases, while horizons limit the region within which this evolution can be traced. The horizons of the observable universe highlight that cosmology deals not only with objects and processes, but with fundamental limits to knowledge itself. And this is not just a problem for the distant future. Modern cosmology faces more urgent mysteries, discrepancies that cannot be explained even today. Inconsistencies in the data do not disappear as instruments improve. On the contrary, they become clearer. The history of science shows again and again that such persistent discrepancies, which cannot be dismissed as random errors, often precede major discoveries. As observations accumulate, the picture of the observable universe becomes more detailed, but at the same time, discrepancies between different data sets and theoretical expectations become more apparent. In cosmology, such inconsistencies are not seen as errors in themselves, but as possible indications of an incomplete current description. The most discussed example remains the difference in estimates of the rate of cosmic expansion obtained by different methods. Measurements based on nearby astronomical objects give one value, while analysis of the cosmic microwave background and the early state of the cosmos gives another, and the difference between these estimates exceeds expected statistical deviations, persisting even after all possible checks and refinements. One interpretation allows for hidden systematic effects in distance or brightness measurements. Another suggests that the standard cosmological model is incomplete and needs to be expanded. In this case, the difference may reflect the influence of additional physical processes that manifested differently in different epochs of the universe's evolution. In addition, anomalies in the distribution of the cosmic microwave background on the largest angular scales are discussed. Some features of this distribution appear less symmetric than expected in a simple model. The statistical significance of such features remains a matter of debate, as the number of independent measurements at these scales is limited. Another area of discrepancy is the growth of cosmic structures. Observations show that the rate of formation of galaxy clusters may differ from predictions based on parameters extracted from analysis of the early background. These differences are not catastrophic, but they are systematic. And possible explanations include both refinements to the properties of dark energy and changes in the characteristics of dark matter. The choice of statistical methods also plays an important role. Cosmology operates with a limited amount of data, especially at the largest scales, so rare fluctuations can significantly affect conclusions. Distinguishing between random deviation and a sign of new physics requires careful analysis and comparison of independent observations. It should also be considered that different observational methods are sensitive to different aspects of cosmic evolution. Observations of the nearby universe reflect relatively late processes, while the cosmic microwave background records the early state. If changes not accounted for in the model occurred between these epochs, they may appear precisely as discrepancies between datasets. Anomalies and tensions in the data do not mean that the existing picture is wrong as a whole. Rather, they point to the limits of simplified descriptions. And each new persistent inconsistency highlights that even with a high level of agreement between theory and observation, there remain areas where understanding is incomplete. Perhaps the issue is that the physical laws we use apply only under certain conditions. The theory of gravity perfectly describes the motion of planets and galaxies. Quantum mechanics, the behavior of elementary particles, but uniting them in a single description has not been achieved for more than 100 years. And without this unification, it is impossible to truly describe what happened at the very beginning, when the universe was so dense and hot that both approaches should have worked simultaneously. In cosmology, this problem is especially acute. The early universe and regions of extreme density require both theories at once, which are still incompatible. Cosmology relies on physical laws formulated and tested in conditions far from the extreme states of the early universe or the depths of cosmic space. And these laws show high accuracy in describing processes in laboratory conditions, within the solar system, and at the scale of galaxies. In standard models of the universe's evolution, the equations lead to states where physical quantities reach extreme values, and such results are usually interpreted as a sign that the theory has exceeded its range of applicability. This means that the description ceases to be reliable long before those extreme conditions are reached, and cosmological models inevitably contain regions where they work only as approximations. Even in later epochs, the question remains whether physical constants are truly unchanging. It is assumed that fundamental parameters, such as the speed of light or the characteristics of fundamental interactions, are the same throughout the observable cosmos and all its history. This assumption fits available observations well, but direct checks on cosmological scales are extremely limited. Small deviations could go unnoticed, yet significantly affect data interpretation. Some observations allow for the possibility that the properties of dark energy, or even the form of gravitational interaction, may change over time, though such effects have not yet been confirmed. There are also questions related to the symmetries underlying physical theories. Many models assume certain symmetries of space and time, simplifying the description of processes. Yet the observable universe shows symmetry violations at the level of structure and evolution. It is unclear whether these violations are fundamental or arose from spontaneous processes in the early history of the cosmos. The limits of the law's applicability also appear in the interpretation of observational data. The same observations can be reconciled with different theoretical approaches if the assumptions about matter and space behavior are changed. And this means that cosmology often deals not with unambiguous conclusions, but with classes of admissible models, each describing the data within certain limits of accuracy. The places where the description becomes uncertain or contradictory do not indicate a lack of data, but the limits of our current theoretical tools. And these limits create space for new ideas. And if the laws themselves have limits of applicability, what does that say about our knowledge of the universe as a whole? We can study only one instance of the universe, the one we live in. There is no way to run a control experiment, no way to compare with another universe. All knowledge of the cosmos is drawn from observations of a single point in a single era. Unlike other areas of physics, here it is impossible to change initial conditions or repeat observations in independent regions. And this makes data interpretation especially sensitive to initial assumptions and statistical analysis methods. Even with the greatest care, the observable universe remains only a part of a broader reality that science can judge only indirectly. The very concept of observability introduces constraints not due to lack of effort or technology, but due to the fundamental properties of space, time, and information transfer. The observable region is not necessarily typical or representative of the whole. Current models assume it has no unique properties, but this assumption cannot be directly tested and serves only as a methodological basis for building theories. All conclusions about the universe's properties are based on data from a finite region of space, and that region is not necessarily typical. There are theoretical approaches that suggest the observable universe is just one realization of a broader structure. In such models, the properties of space, physical constants, and initial conditions may vary in different regions. These ideas arise as attempts to explain why the observable universe has precisely those parameters that allow for complex structure and long evolution. But such concepts are hard to test as they go beyond what can be observed. Even without such models, the question remains of how fully the observable universe reflects the laws governing the whole. Perhaps some effects manifest only on scales far beyond what is accessible to observation. The observable universe also changes over time. Objects we can observe today will not be the same as those available in the distant future. This means that cosmological knowledge itself is subject to historical evolution. The picture of the cosmos depends on the era in which the observer lives, and on which signals have not yet disappeared beyond the horizon. At the same time, scientific description does not strive for a final answer. It is formed as a system of interconnected statements, each with its own domain of applicability. In cosmology, the distinction between what is confirmed by observation, what follows from theoretical models, and what remains an assumption is especially clear. Maintaining this distinction is an important part of the scientific approach. The observable universe appears as a coherent but incomplete picture. It allows us to reconstruct the history of cosmic evolution, identify patterns, and formulate questions that go beyond available experience. These questions do not indicate a lack of knowledge. They point to the natural limits of any description based on observation. In this sense, cosmology not only investigates the structure of the world, but also demonstrates how science works with uncertainty. It builds models, tests them against available data, and clearly marks the limits of their applicability. And that is its strength, not its weakness. The observable universe remains a space where the known and the unknown coexist, forming a whole that is open to further understanding. Please let me know in the comments how this story felt to you. It truly matters to me to know if it resonated. What do you think? Should science keep searching beyond the observation horizon, even if the answers there are fundamentally unreachable? Or is it more honest to accept the limit and focus on what is accessible? And also, do you find it more comfortable to watch a horizontal video sequence or a vertical one for your phone?